Okay, so I'd like to thank Jamie for the nice introduction, and I'm going to tell you about the smallest drops of the hottest matter, some new things that I think are very exciting that we've been doing at RHIC. So I think we have to set the scale, and I promised you the hottest matter. Well, how hot is it, right? Well, right now it's been awfully cold, but if you can imagine a nice sunny day at the beach, that's about 80 degrees, right? Lava, which is pretty hot, right? Molten rock, that's about 2,000 degrees Fahrenheit. The center of the sun, that's really hot. That's 28 million degrees Fahrenheit. If you were to look at the hottest thing that you can find in the cosmos, that's the core of supernova. And that's about 150 billion degrees Fahrenheit. So we're quite a ways away from a sunny day now. But what I'm going to tell you about is the quark-gluon plasma, and that's about 5 trillion degrees Fahrenheit. And as I hope you'll understand by the end of this talk, there's no picture that I can show you. Just the ways that we are able to access it with the data and what we've been doing. So let's start with the nucleus. 99% of the mass of atoms, and thus all the matter that you see around you, the normal matter, is really in the nucleus. And the nucleus is composed of two things, which are protons and neutrons, which I've illustrated here by the blue and the red balls. And the nucleus is held together. What keeps these protons and neutrons together is called the strong force. And it's one of the 4 fundamental forces in nature. So there's gravity, which we all know about. There's electromagnetism, which governs a lot of the stuff that you see around you, electronics, chemistry. This is all electromagnetism. There's the weak force, which I'm not going to talk about. And the 4th force is the strong force. And it's characterized by, get this, strong interactions, and they're very short range. So what's inside these protons and neutrons? What are they made up of? Because they're not actually... they're not point particles, they have a structure. And if you may have learned at some point along the way, protons and neutrons are made up of 3 quarks, which I've illustrated here by the Qs. But if you look a little bit closer, they actually have more quarks, antiquarks, and gluons. So they have this rich structure, which I've attempted to allude to by adding more things to the circle, but it's really just a cartoon here. And this is what makes up protons and neutrons. They're just big piles of quarks and gluons. And the interesting thing about the strong force is this property called confinement. And so this idea that you could have, a quark just sitting off by itself, like you can with an electron. You can't have that with the strong force. It's called confinement and is one of the defining features of the strong force. And so this confinement actually makes the strong force very tricky to get your hands around because you can't study it in the way you can with the electromagnetic force. You need to have clever other ways to study what goes on in the strong force. And so that's what I'm going to tell you about, how we study the strong force using the Relativistic Heavy Ion Collider. So what we want to do is we want to study the strong force specifically at very high temperatures. So what we want to create, what the goal of RHIC has always been, is to create a system that is hot and dense enough for the quarks and gluons not to be confined anymore, so that they wouldn't know what proton or neutron or other particle that they're part of. So the basic recipe for doing this is to take a nucleus, which is again composed of many protons and neutrons. I'll add the laser pointer here. And add a whole lot of energy to make it very hot. Well, so how are you going to do this? What are you going to do? You can't just put it on a Bunsen burner. You have to find another way. And so what we do is we take 2 nuclei and we actually smash them together at over 99 point a lot the speed of light. And this is the goal. The goal is then to create a system that has so much energy in it that this enables us to achieve high enough temperatures to break this confinement that is characteristic of the strong force. And we call that system generically the quark-gluon plasma. So to do this, it's a very small system, but you actually need huge accelerators. And there are 2 places in the world that you can do this. One is RHIC, and one is the Large Hadron Collider. So RHIC is, of course, here at Brookhaven. We are somewhere over here at Berkner Hall right now. If you go out, the RHIC ring is over there. It's in the woods. And so we have collided a lot of gold-gold collisions at 0.2 TeV is a collision energy. Now, the LHC is in Switzerland and France, and they're, of course, famous for, among other things, discovering the Higgs particle last year. But what else they do is they actually have a program where they collide large nuclei together. We collide gold, they collide lead. Lead's a little bit bigger, but qualitatively it's the same. What is different about the LHC is that they have a much higher collision energy. So they can collide these lead nuclei at 15 times higher energy than we can at RHIC. And so then the combination of RHIC and the LHC gives us an interesting way to really study the properties of this matter by changing the temperature that it's created about. So we're colliding these very small nuclei together. The nuclei are very small and they're very dense. We're attempting to create the quark-gluon plasma. And to set a basic scale, it's really small and it doesn't last very long. So I tried to figure it out. It lasts for a billionth of a trillionth of a second. And it's a billion times smaller than the pixel on an iPhone display. This is the iPhone 5S is where that spec comes from. So it's pretty small. So this is why, of course, you can't get a picture of it, because how are you going to get a camera that works that fast or something that has fine enough resolution? So this makes it fun as an experimentalist, because, which I am, because you have to be clever in order to understand what's going on here. Or at least you have to try to be clever. So what do we see? What is our handle on what goes on in these collisions? Well, hundreds or thousands of new particles are created in each and every collision. So this is two nuclei, they come together, hundreds or thousands of new particles are created. And you might have heard of E equals mc squared. That's exactly what happens. All this energy that comes in from the speed of the nuclei from the collider is then turned into a quark-gluon plasma, which then cools off and becomes new particles. So this is supposed to illustrate a sea of particles flying out of a quark-gluon plasma that is expanded and cooled. And this blob of particles is what we have access to. And these particles provide the only window that we have. And we look at each collision individually. So two nuclei collide. We look at that event all by itself. But we actually measure billions of collisions. So it's a statistical process to try to figure out what you can infer from the hundreds or thousands of particles in each collision a billion times to try to figure out what's going on. So we use the Relativistic Heavy Ion Collider, and this is just a bigger picture. And the point I want to make with this plot or this picture is to just show you that what is overlaid here with these lines is actually the accelerator complex for RHIC. It's not just the big ring out there in the woods. It's a bunch of different machines that go together to start the ions at a low energy, to accelerate them at the AGS, which is actually responsible for 3 Nobel Prizes at Brookhaven, and we use it as a booster, essentially, to bring the ions out to RHIC, where they are brought into collision now at 2 points. Jamie alluded to the 2 detectors at RHIC. So one is the star detector, which is over here, and one is the Phoenix detector, which is over here, and that's the one I work at. So I get to show you a picture of Phoenix. What you get from this plot, or this picture, is that it's big, hopefully. This is a person right here. I hope you can make that out. So that really sets the scale. It's huge. It weighs about 3,000 tons. What happens is, first of all, I should note that it's taken apart to work on it. When it is in a data-taking mode, all the pieces come together. They fit together like a puzzle very tightly. But for illustration here, see, we have a beam that comes in here and another beam that would come in this side, and then the collision would happen right here in the middle of this magnet where you can't really see. And so then the particles are these white lines, things that would come out this way. And what we do is measure them in here, which is it's a drift chamber. It was built at Stony Brook largely, and it measures the momentum and the angles of the particles that come out. So if we go back to a schematic picture, you have an incoming nucleus here, an incoming nucleus here, a whole bunch of particles that come out here. And now I will show an event display from the star collaboration. This is what you see in a single collision where the nuclei mostly hit each other head-on. And so these are these hundreds or thousands of particles. Each one is represented by one of these blue or green lines. And so this is what looks like a mess that we have to try to tease the physics out of. So this is where the nuclei come in like this. Well, what if you rotate that 90 degrees? You can see there's a cylindrical symmetry. So this is where the one beam is going into the screen and one beam is coming out. And you see the particles are emitted really in all different directions. Now, while you might think that these nuclei are so incredibly tiny that all collisions are the same, they're not. And what I want to talk a lot about is the geometry of these collisions. So if we look, we'll keep this view of one nuclei going into the screen and one nuclei coming out. And what I've shown here are simulations of what 3 different collisions might look like. And so over here on this side, first of all, each one of these circles is a proton or a neutron. It doesn't matter which. The ones in blue are from one nuclei, and the ones in red are from the other. And so this one here shows one where the centers of the nuclei are displaced from each other. So you can see these hollow circles are the ones where parts of the nuclei didn't interact. So they missed the other nuclei. And these dark ones are the ones where the protons and neutrons actually participated in the collision. So what happens is that these bits that are shown in the open circles, they would just keep flying away at nearly the speed of light, and they would be gone. And what's left is here. So you see the overlap region here is largely elliptical. As the centers become closer together, you see something that's a little more circular here. And as the centers are very close together in this collision, you see that the whole thing is pretty much circular. Most of the protons and neutrons are participating in the collision. Yes. So this is, as I was saying, the parts of the nuclei that don't overlap. They don't play a role in the collision. They're called actually spectators, and they just move on. So what happens when you take this geometry and you look at it a little bit closer? So we're just going to take in the same event display before, and I've imposed a coordinate system on it, and I've just defined an angle. And so this angle we'll just call phi. And the interesting thing is, what makes you believe that we're actually sensitive to something about the geometry is if you know this angle phi, and you just start to count the particles that come out with respect to that angle, it's a meaningful quantity, and that's what's shown here. This is just the relative number of particles that come out with respect to this angle phi. I'm sorry, this is in radians here, so this is 0 degrees. This is pi and minus pi at the end, so that would be over here. And pi over 2 is here, and that's these dips here. So what you see is you have more particles, about 20% more particles that come out this way and this way than come out that way and that way. So I've taken away this to make it a little easier to see. So this ellipse actually seems to be a meaningful quantity. So here's the nice animations. So you have 20% less particles that come out the short sides of the ellipse than come out the long side. So what does this tell you right away before anything else happens? It tells you that the interactions between the particles are important. So I've just drawn a little ellipse here, and I've put a few back dots to illustrate whatever kind of particles might make up a quark-gluon plasma or anything. And you can see if they're very dilute, they don't know where the other particles are, because in any direction that they're going, they're not going to hit anything else that comes out most of the time, right? If this one goes this way or that way or that way, there's a whole bunch of ways that it could be going and not know anything else about the geometry of the collision. It just doesn't see anything else that goes on. Now, as you start to add more and more dots, you can see qualitatively that now it's easier to see what goes on. This particle knows about this particle, probably knows about that one. If it goes that way, it hits something almost certainly. It's only if it goes this way that it doesn't hit much. And so if you keep adding more and more, so this is really a gas picture where you can think of discrete particles. But actually with the quark-gluon plasma, what's interesting is you have to think of it as a liquid rather than a gas. It's hottest and it has the highest energy right here in the center of the quark-gluon plasma, and that becomes less so as you go out towards the periphery where there's less things that were involved in the collision. So it wants, you have high pressure here, low pressure out here where there is nothing. And so this is steep pressure change going out the short sides, and a large pressure change, or a gradual pressure change going out this side. And so I kind of wanted to think about it as, you can imagine if you're at the top of a mountain, maybe there's 2 ways you can go down. One, you could jump off the cliff, and that is going out the short sides here. And one is you could walk down the nice 4-hour hike, and that's really going out this way. So this is steep, this is gradual. So you can see what we're describing the quark-gluon plasma as is not like a gas, but is a liquid. And what characterizes liquids? Well, they flow. So there's low viscosity liquids, like water is a relatively low viscosity liquid. And there's honey, which is a high viscosity liquid. It doesn't flow. If you drop a rock in water, you can see ripples that emanate out. You drop a rock in honey, well, it's just going to sink to the bottom. So we have a liquid quark-gluon plasma, and we want to understand that in terms of its liquid properties. So the quark-gluon plasma flows well. We're able to take this initial shape and turn it into what you see in these final state particle distributions. There's a connection between here and here. So that's telling us that it's more like water than honey. So you can describe the viscosity of a liquid in terms of a quantity called eta over S, which is for technical terms, is the shear viscosity to entropy density ratio. And so water has an eta over S of, it's greater than 25. These things depend on things like temperature or pressure. The quark-gluon plasma, what we know from models that have been created by people here, among other places, is that the eta over S of the quark-gluon plasma is actually less than 5. And this is actually very interesting because there's a calculation from string theory that there ought to be a universal minimum for these kinds of, for viscosity, and that should be 1 in this units of 1 over 4 pi. So what we have is an upper bound for the viscosity of the quark-gluon plasma, and it's actually very close to this calculation from string theory. This is a connection that wasn't anticipated when they turned on RHIC. And so what we want to know is the quark-gluon plasma viscosity, is it close? How close is it to this lower bound? Does it actually go below? I mean, this is a calculation. Can we measure it? Is it close? We're looking at a very low viscosity fluid. So what we want to do at RHIC is we want to determine the viscosity of the quark-gluon plasma, how it depends on temperature, and this is really one of the central things that we're trying to get at. So we can change the shape and change the particle distributions, and this is really one of the ways that we try to get at the viscosity of the quark-gluon plasma. So if a collision like this, which is more of a glancing collision, which has an elliptical shape, you see this large asymmetry in the particle distributions that I already talked about. If you look at a collision like this, which is more circular, you see a much smaller, this one's less than 10% here, asymmetry in the particle distributions. And these particle distributions, I should note, are for many, many events of the same type of impact parameter. So it's not just one event, which is why the error bars on these are so small, because you just count particles for a lot of events. And so this is where the interaction between RHIC and the LHC really becomes interesting, because you can look at the number of produced particles. I told you it was in the hundreds or thousands. It depends on the type of the impact parameter of the collision that you're looking at. And as the collisions become more and more circular, you make more and more particles, and that's just because more and more stuff happens in the collision. So this is at RHIC. So you go from these elongated collisions where fewer particles are produced to these more circular collisions where a lot of particles are produced. Now at the LHC, I told you they have a 15 times bigger collision energy. So they have more energy, so they can make more particles. So for a given number of produced particles, there's a different shape for collisions at the LHC than there is at RHIC. And so having this big jump in collision energy is actually really beneficial to try to understand the physics of what's going on, the connections between the shape and the particle distributions that we see. So I tried to keep the math to a minimum for this type of talk, but I have to have one quantity, and I'm going to call it V2, which is really the strength of this modulation. So V2 is related to the size of this deviation from a flat line. So this would be a large V2, and the one that I showed you that was much flatter, that would be a small V2. So we measure V2, then as a function of the number of produced particles at both RHIC and the LHC. So that the purple is the LHC at the higher collision energy, and the blue is at RHIC at the lower collision energy. And what you see is that the V2 is different at RHIC and the LHC as a function of these number of produced particles. But of course, I also told you that the geometry is different. The shape of the collisions at the same number of particles is different between RHIC and the LHC. So how are we going to quantify this shape? Well, you can just use a quantity called eccentricity. And it's basically how elongated any shape is. So you have a circle. That has an eccentricity of 0. If you have a line, that has an eccentricity of 1. That's what's shown here. And then in between, as you get more and more elongated, the eccentricity obviously increases. So this is we can calculate this for any given class of collisions. We can figure out what the average eccentricity is. And then you can just take those V2s that I showed you on the previous slide, and you can divide them by the eccentricity. And you can see while the curves were different before, dividing them by the eccentricity brings them together. This is telling us that these particle distributions that we're seeing are actually sensitive to something that happens in the geometry of the collision. And that's really, I think, pretty amazing considering these collisions are so incredibly small. We're measuring them with these big detectors. We're measuring something that's sensitive to something like 10 to the minus 15 meter scale geometry variations. So this relationship between the geometry, epsilon 2, and the V2 is really a signature of the small viscosity quark-gluon plasma. If it had larger viscosity, this wouldn't work. If it was an ideal gas, this wouldn't work. So the question I want to talk about, and I promised you before this lengthy introduction, was really how small can the quark-gluon plasma be? And you might think this is kind of a silly question, right? Why take something that's really small? I already told you it was a billion times smaller than a pixel on an iPhone. And why would you try to make it even smaller? I mean, unless you were just a masochist, really. So changing the size and the shape of the quark-gluon plasma is actually going to help us measure the viscosity. All right, so this is these big nuclear collisions that I was telling you about. These could be gold nuclei colliding or lead nuclei. So what if you take that and you just take one of them away and you replace it with a single proton? So now you have one proton and it's hitting this. The question is, can you make a quark-gluon plasma in this sort of description like you could in the other, in these big nuclear collisions? And that's actually a question that is very surprising and potentially can tell us quite a bit about the viscosity and what it takes to make a quark-gluon plasma. And so this is a question that a year and a half ago maybe wasn't on everyone's mind, but then there were these very interesting measurements that came out of the LHC, which actually measured a V2 in proton-lead collisions. And this was, I think, very surprising. And what you see is that the plot looks qualitatively like what I showed you for the heavy ion collisions, for the gold-gold and the lead-lead collisions. This, again, is a function of the number of produced particles. And you see this ratio V2 over the eccentricity increases as you go to more and more particles. It looks a lot like the gold-gold and lead-lead ones that I showed you before. Now, the interesting thing here is that this whole idea of geometry that I was talking about, it's a little bit different when you're colliding a single proton on a giant gold or lead nucleus. So here we can vary the impact parameter, and you can get things that have a large eccentricity. So a very oval-shaped quark-gluon plasma, and you can turn that into a big V2, it seems. Now, with a single proton, it's only going to hit a very small amount of the lead nucleus at the LHC. And so it's going to be roughly circular, modulo any fluctuations that might occur. And so the question that, of course, people wanted to ask as soon as we saw these measurements is, well, is there any way you can change the geometry to really understand if this relationship between the geometry and the particle distributions that we saw in the heavy ion collisions, is there a way we can access that in a system that's like these proton-lead collisions? And actually, there is. You can imagine, of course, qualitatively, what if you just added a second proton or neutron to the smaller nucleus? Then you could go from something which is to first order circular to something which is first order elongated. It has a large eccentricity, just like those large impact parameter gold-gold and lead-lead collisions I was talking about earlier. And actually, it was very fortuitous. RHIC had taken D-gold data for other purposes, and we were able to then analyze this data to look for a V2. And so it's deuteron gold collisions. And a deuteron is just the next most complicated nucleus up from a proton. It's if you take a proton and you add a neutron. And so this is really a 2-nucleon nucleus. That's what you see here. Now, I'm going to go into a little bit of technical details. Jamie mentioned two-particle correlations. This is part of what I do. Which way does the ellipse go? When the ellipse is really big, like in these gold-gold collisions, we think we can measure the angle that defines the ellipse, that defines the zero of this angle phi. We can measure that pretty well. When the things get pretty small, which way does the ellipse go? This is just the same collision that I've rotated in 3 different ways. Where is the ellipse? Does it go this way? Does it go this way? Does it go that way? We can't control it. This is something we just have to take the collisions as they come. And it's actually really hard to measure for these small systems. So what do? We do things where we look for correlations between the pairs of particles. And here we really take advantage of the fact that any particle that comes out of a collision knows way more about the collision than you do because it was there and you weren't. So we use the correlations between pairs of particles. So we define this angle delta phi, which is just the angle between any 2 pairs that come out of the collision. Of course, there's lots of reasons for particles to be correlated. I could give you a whole hour-long seminar on that, but I won't bore you with the details. I will just tell you that this is this delta phi variable, and this is for the signal plus the background. And the blue line is for what we think an estimate of the background is. And so the first thing is that you can see that the signal's not so bad here. It looks like there's signal here in delta phi and here, and it looks like there's sort of anti-signal down here. The signal plus background is definitely bigger or different than the background. So we have the possibility of making a measurement. So if you just subtract these two quantities, which is what we did, what you see are the solid blue points here, the signal minus background, again as a function of this delta phi. And what you see is it has a shape that's reminiscent of the one that I showed you for the particle distributions before. And actually, the magnitude of this blue curve then is related not to V2, but to V2 squared. So it comes in V2 squared times the cosine of 2 times this angle. And so you can extract V2 from looking at these two particle correlations. And that's exactly what we did. So I showed you, this is the same plot I showed you before with the proton-lead results from the LHC. So it's V2 divided by this eccentricity measure. So if the deuteron-gold collisions provide you with something that is sensitive to geometry, then you expect to have a V2 over epsilon 2 for the deuteron-gold collisions. It lies roughly within this box. Now, I've just drawn it with PowerPoint. I think it should be obvious to people who are experimentalists themselves that there's systematic uncertainties that go into the determination of various quantities here. We don't necessarily expect the scaling to be perfect. These are statistical errors here. So I've drawn this box to sort of guide the eye as to where you might expect this to be. And so when we measured the V2 over epsilon 2 in the deuteron-gold collisions, it actually came out here, which is inside where I drew the box. And that was actually very exciting. It suggests that the V2 that we see in these very small collision systems, both at RHIC and the LHC, is sensitive to something about the geometry of the collisions. And actually where it gets shocking is when you now take these deuteron-gold points and proton-lead points that I showed you before and just add them to the plot that I already showed you for the gold-gold and the lead-lead. So this is the deuteron-gold points and lead-lead points. They're over here. They're shown in the blue, the green, and the yellow. These are the heavy ion points. They're over here. I think the important point is that if I took the legend off and made all the points the same color, you wouldn't be able to tell the difference. You wouldn't be able to know where the quark-gluon plasma is supposed to start or stop. If you look at it in this way, it really seems that you see continuous behavior from very large systems at the LHC to very small systems at RHIC and the LHC. So this is, I think, very interesting and very suggestive. I think I want to talk a little bit about how the particle distributions, they actually reflect the initial shape of the collision. I hope I've convinced you of that by now. In both big and small collisions, you can take the geometry of what you see, and you can map it onto the shape of the particle distributions. One of the interesting things is that each nucleus is a little bit different. Remember, this is a quantum mechanical system. So these nucleons, or these nuclei are actually composed of about 200 protons and neutrons, the gold nucleus and the lead nucleus. And so they each look a little bit different. These nucleons, or these protons and neutrons, they move around inside the nucleus, and the collision captures what goes on at a single instant in the collision. So you're sensitive to really the quantum fluctuations of the positions of these protons and neutrons. And so these are 3 simulations of what a gold nucleon might look like in the same manner that I've been showing you for a while now. And you see, by and large, they look the same. There's nothing particularly special about any of them, but you can see if you look at the edges that they're different. This one's different than this one, then it's different than this one. So if you take 2 fluctuating things and you smash them into each other, then of course not only each nucleus is unique, but each collision is unique. So I showed you a lot of pictures that had perfect ellipses and they looked very nice. But if you go and you look through simulations of these things, you can find collisions that don't look very nice at all. Here, there's one of these collisions with the large impact parameter like I showed you before, only this time the ellipse doesn't really seem to line up, and it's got this weird little thing. This one over here, I actually don't know what it looks like, but it's funny looking. This one I thought was particularly interesting because the ellipse not only lines up it goes over this way. But it also has these 3 little islands, essentially, which would be like hot spots. Little mini quark-gluon plasmas could form there. And so you're really looking at these fluctuations when you look at each collision. The collision doesn't know what a typical collision ought to look like. It only knows what its own collision looks like. So describing it in terms of just this elliptical shape, like I've been talking about for quite a while, is not sufficient, because you have to take into account these fluctuations. So there's actually all kinds of different shapes that you can pick out, not just the elliptical shape, but you could pick out a triangular shape, square shapes, and even higher order type shapes going on and on. So you could describe each one of these shapes by some of this, some of this, some of this. You'd have to add them up, rotate them a bit, and try to figure that out. So how can we have shape control in the smaller collision systems? Well, that's actually interesting, because the fluctuations of these large nuclei aren't the issue. It's the number of protons and neutrons that are actually in the small nuclei. So this is the proton-lead collision that I've been showing you for quite a while, and it's roughly circular, so it has a small eccentricity. It's not elliptical. This is a deuteron-gold collision, and it is elliptical. It has a large epsilon 2. So what if you were to try to look for something that had a triangular type shape? Well, you wouldn't do it with a deuteron-gold collision. That only has 1 proton and 1 neutron in the small nucleus. So there's nothing triangular about this. If you take something that looks like a dumbbell, there's no way to turn it into a triangle. It's just not going to work. But of course, you could probably already figure out where this is going. We added 1 nucleus and we turned it into something that was elongated, or one neutron. So what happens if you add another proton or a neutron to the collision? Then you could get something that actually does have an inherent triangular shape. 2 protons and a neutron together, that would have an inherently triangular shape. And you could actually, if this is what's happening to describe the physics, you could imprint a triangular-shaped quark-gluon plasma on the middle of one of these large nuclei. And that's actually pretty exciting. Something that we never anticipated that this would be something we'd want to do, but it actually is. So the deuteron is this elongated nucleus. It has 1 proton and 1 neutron. So a nucleus that is made up of 3 would be helium-3 is one of them. So it's got 2 protons and 1 neutron. There's another one that you could make, a triton, which has 1 proton and 2 neutron, but we're actually interested in helium-3. It's easier to accelerate. So when you have a large flexible collider like RHIC, you can actually do this stuff. And so we put in a proposal last year to measure helium-3 gold collisions. And we anticipate in the next year being able to run helium-3 gold collisions to try to make a triangular-shaped quark-gluon plasma. This is something that was accepted. And so what we want to do is we want to run proton gold collisions, deuteron gold collisions, and helium-3 gold collisions, all at the same, not at the same time, but close together in time, so that the running conditions in the experiment are the same, so the same people analyze the data using the same code, and we really want to understand how the geometry in these very small collision systems maps into the particle distributions that we measure in our detector. And this is something that I personally am very excited about, and I can't wait to analyze this data. This is something that is very new. So I want to talk a little bit about the future, other things that I'm interested in. This is something, the helium-3 collisions are something that we wanted to do in the next year or so. Well, where's the longer-term future of RHIC? What else do we want to know? And of course, a system as complicated as the quark-gluon plasma, you want to look at it in as many different ways as you can. Experimentalists are generally paranoid people. If you see things one way, that's great. If you see things 2 ways, that's better. If you see things as many ways as possible. So this is the Phoenix detector as it exists today. And what we're working on is something called S-Phoenix, which is coming soon in 2020. And it is to replace most of what you see here with a detector that looks more like those that they have at the LHC. And these are really optimized to measure high-energy quarks and gluons that pass through the quark-gluon plasma and act like a microscope to tell us something about the structure of what's going on inside the quark-gluon plasma. So we call this S-Phoenix, and we're working on it. We're very excited about it. This is something that is part of the lab's future, and that a lot of work is going into this. You can imagine if you look at this picture, you see it's very complicated. So putting together a new detector is a very complicated effort that's taking a lot of people and a lot of time. And so 2020, it doesn't seem far off to me. It seems right around the corner. So we're working very hard on it. And so what we want to do is we want to take what we learned from jets and what we learned from this flow that I've been telling you about, and we want to put those together in collaboration with the theoretical community to really understand what these two different ways of looking at the quark-gluon plasma are then telling us about the nature of the strong force at very high temperatures. So I didn't actually talk about why we had this deuteron gold data, but what we wanted to do with it was to investigate the initial state of the nucleus. We wanted to take a deuteron and hit it on a big nucleus and try to learn something about the nucleus before the collision in the absence of a quark-gluon plasma. Now, I just spent quite a while telling you about why we think we might actually be creating a quark-gluon plasma there. So what about understanding the initial state of the nucleus? Well, that's actually something that is in the longer-term future at Brookhaven, and that's to replace a nucleus actually with an electron. And so I told you that the nucleus is the protons and neutrons are not point-like particles. Well, electrons are. So they're a finer scale probe that you can use to understand the initial state of the nucleus. And so to do that is actually, it's easy in PowerPoint, it's hard in reality. So this is a big, longer scale project to actually change the RHIC accelerator so that it is able to collide nuclei with electrons. It goes by the name of RHIC, and it's a large-scale upgrade. This is just a picture. There's a lot you can find out about it on the web. The time scale for this is actually longer than what I told you about for any of this. This is a longer-term project, say 2025. So what we're really interested in doing here is exploring the strong force. And at RHIC, we're doing, in heavy ion physics, we're doing that at extremely high temperatures. That's what we do. So we're creating a picture of the quark-gluon plasma by using the geometry and the variations of nuclei, both at RHIC and the LHC. It's international because we need both systems to really understand what's going on. These very small nuclei are really a surprising and unique control of the geometry. And it's actually something that's great to study at RHIC because we have a dedicated facility where we have the time to put in to look at varying these small nuclei, the protons, the deuterons, and the helium-3. This is something that can't be done at the LHC. So I'm very excited to understand more about this picture in the future. It should be obvious by now that these sorts of endeavors, it's easy to make plots, but they involve hundreds, thousands of people. So I'd like to make a special acknowledgement to all my collaborators. In the Phoenix collaboration, this is a picture of some of them. There's hundreds of them. There's hundreds of people in STAR. There's many people who work on the LHC experiments in heavy ion physics. And of course, the theoretical people, the theorists, they never get together for a picture, but they are, of course, instrumental in making the models that enable us to understand these collisions. So I'd like to thank my colleagues at Brookhaven and to note that we're funded through the DOE Office of Science. Thank you.
By the initial state of the nucleus.
I'm sorry, that's a bit of jargon that I didn't manage to wipe out. It's what the nucleus looks like before the collision. And so you can't have much of a collision. And so electrons are actually a very good probe of exactly that because they enable you to look finely at the nucleus as it exists.
Relativistic terms, or can your calculations?
The Lorentz contraction.
I don't know what you call
All right, well, so they're moving at very close to the speed of light. So whereas if you had a nucleus just sitting here that you could see, it would look mostly like a beach ball. Yes, it would be round. If you accelerate it to near the speed of light, then there's something called the Lorentz contraction, which makes it look a lot more like a pancake. But all these views of the nucleus that I showed you are actually projecting it into exactly the same way, just like a pancake. So we're looking at it where one's going in and one's going out, and the nuclei are actually shortened along that direction. So it's just all these these protons and neutrons get stacked up against each other. And so that's actually the geometry. It doesn't affect the geometry itself.
Physics is international collaboration. So can you spell which countries and which portion participated in this project?
Well, I'm of course going to leave some people out if I do this. There's certainly a lot of Japanese collaboration. There's collaboration from many institutions within the United States. There's collaborations from Europe and Russia. I think that's mostly it. There's Chinese collaboration as well. There's a lot of Chinese collaboration, especially in STAR.
Particular class is experimental or theoretical?
There's certainly theoretical. The theoretical community is very international. There's very international. They're not part of the specific collaboration. So within the Phoenix collaboration, the countries I just listed, those would be experimental collaborators.
So on that plot you showed where you collided deuterium with gold, and you compared it to what happened at LHC, they had 3 data points, and you only had 1. So why aren't there more different numbers of particles?
Well, that's a good question. And it's actually, the Phoenix experiment was never designed to do this sort of measurement. It's not a high acceptance detector. And so where I showed you the signal in the background here, this background that I highlighted in blue here, sorry, let's get the animations right. The background is very substantial, and we actually have to throw away over 90% of the pairs because this is after you've thrown away 90% of the pairs, because Phoenix just wasn't designed to be able to do exact flow measurements in this particular way. That would be improved with S-Phoenix quite a lot. It's just a particular feature of our experiment, and I'm pretty proud of the 1 point that I had on that plot.
Is there any difference between collision with a helium-3 nucleus and a collision with a triton nucleus? Why did you choose the helium-3?
It's my understanding that first of all, there's no difference from my perspective. I'm agnostic as to which one to do. It's my understanding that the accelerator division was interested in developing the expertise for generating helium-3 beams for future programs heading towards RHIC, and that's why it was chosen. But from my perspective as an experimentalist, I actually don't care if they're protons or neutrons.
In the case of the elliptical and the triangular droplets, if they were liquid droplets, they would have a higher vapor pressure in the more highly curved regions. Do you see a large number of particles coming out in those regions?
Well, first of all, we haven't taken the helium-3 data yet. I think that understanding the details of what exactly is going on in these helium-3 collisions, it's going to take collaboration between both the experimentalists and the theorists who build the models that we use to compare to our data. So that's, I think, a question to be answered.
So you talked a lot about particles. For somebody who doesn't know anything about particle physics, can you define what you mean by particles that you measure coming out?
So what they are they're not stable like a nucleus is stable. You can't let them just sit around for minutes like the podium will. But they're things that are, what I'm talking about is specifically hadrons and mostly pions for people who are experts. And they're made up of a bound state of quarks and gluons. That's what I'm talking about. So most of the things that we measure in these plots here are pions, which is a bound state of a up and a down quark, or an anti-up and a down quark together, or the other way around. So it's like a proton or a neutron, only with one less quark. Yes, so the star detector, of course, exists. Oh, I'm sorry. So they were asking if they have 2 detectors. Actually, there's 3 detectors at the LHC. Many of the points I've shown here are from the ALICE detector, which is the dedicated heavy ion detector. And so all 3 of the LHC detectors participate in the heavy ion physics program. At RHIC, we have both Phoenix and STAR. STAR doesn't have results yet that I can put on this plot, but I think that that's work that's ongoing within STAR. So I hope to be able to do that soon. Well, you can actually, so there's 2 things, right? So the beams are actually composed of bunches. And so we know which the bunch the collisions came from. So if 2 bunches collide, we know that what we're measuring comes from this particular bunch crossing. So that means that it's not this one over here or this one over here. It's possible, though, to have 2 collisions within a single bunch crossing. And that would be, there is a rate of that, and that is certainly an effect that we looked at when making this measurement. Since I'm looking at the correlations between pairs of particles, if you start combining particles from 2 different collisions, they can't, in principle, know anything about each other because they're far apart on the scales that are relevant to the collision. So they would actually make the correlations weaker. So they can't mimic a signal in this particular way. But there are other observables that we look at that we worry very much about 2 collisions within the same bunch crossing.
I guess as a follow-up to that, you always had 2 particles that were coming together in the same horizontal plane, but you can imagine where they're offset, and you can recreate some of these circular or smaller number, but still elliptical. How do you handle that? Is that just in your computations?
We measure the particles that go off away from at larger angles with respect to, I don't think I can get the picture up at this point. We measure the particles that, sorry, my laptop's. We measure the particles that come off at larger angles, and in heavy ion collisions, that's very sensitive to the impact parameter.
So if there's no further questions, we've got some wine and refreshments in the lobby, and I encourage you to go in there and have some discussion. Thank our speaker again.
Thank you.